Hello, this is Arsen Vasilyan, and today I'll talk about joint work with Ronitt Rubinfeld on testing distributional assumptions of agnostic learning algorithms. So here's the basic paradigm. Oftentimes, a computational task is hard if your data is worst case, but it's much easier for data that comes from a specific input distribution, such as uniform or Gaussian. And the question we pursue in this work is, where do you go from there? So we have a theorem that says that this algorithm performs great, for example, on Gaussian data or uniform data. But how do you actually go about the question of, is this data uniform or not? Can I use this algorithm in this specific instance or not? So let me go into more detail about the setting in learning theory that we focus on here. So the setting is called agnostic learning, and as I will explain shortly, work in this field often relies on distributional assumptions on the input data. So before going to agnostic learning, let me first review the standard setting of usual non-agnostic or normal learning. So here's the setting. You are given examples, xi, that are labeled by some known labeling function g. And you're promised that this function g belongs to the hypothesis class F. So a very common hypothesis class studied in the literature is the hypothesis class of half spaces. So there is in n dimensions, there is some n-1 dimensional hyperplane, and function is 0 on one side and 1 on the other side of the hyperplane. And the goal is to find a hypothesis F that has error at most epsilon. And by error, I mean the probability that on a fresh sample, this hypothesis misclassifies it. So if it's a little bit off, it's okay. So epsilon is the parameter that tells us how much error are we willing to tolerate. So now let's go to the very well-studied setting of agnostic learning. So here, again, you're given IID examples xi, labeled by this unknown function g, but now you're no longer promised that the function g belongs to the hypothesis class F. In fact, this function g can be anything. And here is what we want to achieve. We essentially want to find the best hypothesis in the hypothesis class F. So more formally, you want the following. Your hypothesis F should be competitive with the best error achievable in the class F. So formally, you want the error of F to be at most c times this best error plus tolerance parameter epsilon. And for c equals 1, the setting is called agnostic learning. And for other bigger c, this setting is called semi-agnostic learning. And in this work, we'll mostly focus on the c equals 1 case of agnostic learning. And this is a very well-studied setting because in many situations, you don't expect your data to perfectly satisfy something in your hypothesis class. So, for example, you can have adversarial noise in the labels. So maybe an adversary is deliberately trying to change a small fraction of your labels in order to foil your algorithm, or maybe the concept class just doesn't perfectly fit the data. And because of that, this is a very well-studied setting. And I know that also generalizes the classical learning setting that we described in the previous slide. So why not always do this? So the problem is that for many high-dimensional concept classes, this task I described to you is computationally intractable. So for example, for half spaces and n dimensions, no algorithm that runs better than to the n, that has runtime better than to the n is known, and there is plenty of hardness results for this model. So is this then hopeless? Maybe agnostic learning is just not achievable. But it turns out that no. the problem of agnostic learning turns out to be much more tractable when we can make assumptions, very natural assumptions on the distribution. So examples of this are your data comes from uniform distribution, or your data is Gaussian, and so on and so forth. And there has been a very large amount of work focusing on this distribution-specific agnostic learning setting. Now come back to our main question. So how do we know, in order to use this work in distribution-specific agnostic learning, how do we know that this distributional assumption actually holds? Now, here's a first idea one could try. First, one could run the agnostic learning algorithm, and then once they get the hypothesis, one could estimate what's the error of this hypothesis we obtained. But here's a problem. If this error is small, then everything is great, and we don't care about the assumptions. But if not, it could be big for two different reasons. First reason is that maybe the distributional assumption is wrong. There is a hypothesis in your hypothesis class that fits the data really, really well, and you just didn't get it because the distributional assumption doesn't hold, so you cannot apply this theorem that the algorithm achieved the guarantee of agnostic learning under the distributional assumption. And the other possibility is maybe the best hypothesis is pretty bad. Maybe your adversary indeed corrupted a very large fraction of the labels, so there just isn't a better hypothesis in your hypothesis class. And this approach works for the realizable setting, but for the agnostic setting, you don't know when you get the error of your hypothesis that you obtained from the algorithm. You don't know what to compare it with. You don't know what's the optimal error in the class. So because of this, this approach doesn't work. If you want to see if you can trust the output of your agnostic learning algorithm. So the next natural question is, what about you use an off-the-shelf algorithm for testing, for example, uniformity? And indeed, the uniformity testers have been very well studied in the literature. And there, if you want to use one of them, you'll have two challenges. So first challenge, which is not as serious, is sufficiency. So any, for example, uniformity tester that uses finitely many samples will necessarily accept some distributions that are slightly imperfect, that are not exactly uniform. And then the question is, does the learning algorithm still work under such distributions too? And the much more serious problem is the challenge of sample complexity. So it's known that high-dimensional uniformity testers requires tons and tons of samples. So, for example, in n dimensions, the uniformity tester on 0, 1 to the n requires exponentially n samples. And this is a big problem because this agnostic learning algorithms I was talking about, they tend to have much, much faster runtimes. So for example, agnostic learning of half spaces under the Gaussian distribution can be achieved with only n to the 1 over epsilon squared samples, which is much, much faster. So here's the idea. Instead of testing with respect to the, for example, total variation distance, as this aforementioned testing algorithms from the literature do, we will test that the data is just good enough for the algorithm to work. So specifically, here's what we want in our framework. If the data passes the tester, then that is good enough for our learning algorithm to have a good guarantee. And if the data actually satisfies the assumption, it actually comes from this nice distribution, then we want the tester to accept. And here's the formal version, a more formal version of the definition I alluded to. So we introduced the framework of a tester-learner pair for a concept class F under the distribution D assumption. So again, if the data is actually distributed according to the D assumption, then the tester should likely accept it. And on the other hand, if the distribution is such that the testing algorithm is likely to accept it, then if you use your learning algorithm A, it will satisfy the agnostic learning guarantee. So the hypothesis it will output will have an error at most opt plus epsilon, where opt is the error achieved by the best function in the hypothesis class. So in this work we show that tester-learner pairs indeed exist for half spaces under the Gaussian distribution in n dimensions and under the uniform distribution on n-bit vectors. And our tester-learner pairs have combined sample complexity as well as runtime of n to the O tilde 1 over epsilon to the fourth. So in that sense, the sample complexity and runtime of our algorithm is close to the runtime of the agnostic learning algorithms for half spaces that do not need to test their assumptions. So let me talk a bit about the ideas that go into design of our tester-learner pairs. So here's two ingredients that are important for us. One, specifically right now I will focus on the tester-learner pair on the uniform distribution, and the tester-learner pair for the Gaussian distribution is quite similar. So first we use the tester for k-wise independence, and one could use the algorithm of Alon Goldrake-Mansour or Alon Andoni Kaufman Matulev Rubinfeld Xie. And so unlike uniformity, which requires something like 2D samples in order to test, the k-wise independence can be tested only in time something like n to the k. So poly 1 over epsilon wise independence can be tested with runtime only n to the poly 1 over epsilon, where up to total variation of epsilon. And the second ingredient that's very important to us is the agnostic learning framework of Galay, Kleibans, Mansour, and Tirvedia for 2005 that uses low-degree polynomials in order to agnostically learn concept classes. And in order to analyze this tester-learner pair, we need the following. So prior to our work, it was known that half spaces are well approximated by low-degree polynomials relative to the uniform distribution. But in fact, we need a stronger novel statement in order to analyze this particular tester-learner pair. So we need to show the stronger statement that every half space is well approximated by a poly 1 over epsilon wise poly 1 over epsilon degree polynomials relative not to just uniform distribution, but any poly 1 over epsilon wise independent distribution, which is stronger. And this novel statement is very crucial in our analysis. All right, so we have this new tester-learner pairs for half spaces that has the Gaussianity assumption and uniformity assumption that are good for agnostic learning algorithms to be used. So is it true that this can always be done? Whenever we have a distribution-specific agnostic algorithm that's fast, we can also have a good tester-learner pair? And turns out no. And we show strong separations for this type of question. So for the class of monotone functions on the Boolean cube 0, 1 to the n, as well as the function class of convex sets when your distribution is Gaussian in n dimensions, For these two classes, there were algorithms for agnostically learning them using something like 2 to the square root n samples at runtime. And we show that if you want a tester-learner pair, if you want to test this distributional assumption and still learn these function classes, then the combined runtime and also sample complexity of your tester-learner pair has to exceed something like 2 to the n. So there is a price one probably has to pay in order to test assumptions for these two function classes of monotone functions over the n-dimensional Boolean cube, 0, 1 to the n, and the convex sets in n dimensions under the Gaussian distribution. And we know that's pretty strange because in order to learn those classes, a very similar algorithm was used as the one for learning half spaces. Specifically, this is the algorithm of low-degree polynomial regression. And so what's so different between half spaces and monotone functions? So let's go back to this statement that was crucial for the analysis. So we showed that every half space is well approximated by low-degree polynomials under poly 1 over epsilon wise independent distribution. So for monotone functions, it was again known that monotone functions are well approximated by low-degree polynomials relative to the uniform distribution. But is it true that monotone functions are also well approximated by such polynomials under something like square root n wise independent distributions? And that's what one would need in order for the aforementioned tester-learner pair to also apply for this class. And here it turns out this is not the case. That this statement is false, and it's even false for distributions that are not square root n wise independent, but even n to the 0.9 wise independent, and so on. So, and this is the key difference between half spaces and monotone distributions that allows one to design tester-learner pairs for half spaces, but not for monotone distributions. And this turns out to be very connected to this notion of fooling and pseudo-randomness, where you want to use a k-wise independent distribution to see which fraction of elements on the cube on the 0, 1 to the n are labeled 1 versus 0 by the function. And there it was already known before our work that monotone functions and half spaces are very different, because monotone functions cannot be fooled by k-wise independent distributions, and half spaces can be fooled. And this connection has been made much more explicit in the work of Golagota-Kothari-Klivans 2023, that's also presented in this conference. And they show provably that result from pseudo-randomness about fooling of a function class can be translated into a tester-learner pair for this class. And finally, I would also like to note that this description for monotone functions applies absolutely analogously for the class of convex sets under Gaussian distribution. So there again, the class of convex functions can be well approximated by low-degree polynomials, but under the Gaussian distribution, but not under a distribution that looks like Gaussian when you only restrict to them to subsets of small number of variables. So we also know that this lower bounds we prove also rule out standard agnostic learning algorithms for various for monotone functions and convex sets under various quite natural classes of distributions. So for example, it follows immediately from our lower bound that you need something like to the n time to learn monotone functions under distributions that are close to n to the 0.99 wise independent. So this thing is of independent interest. And Finally, I'd like to note that since this work, there's been a lot of other work showing more results in this framework. Golak Godar and Clivens, which also presented the same conference, make numerous improvements on our work. So they give tester learner pairs that are more efficient. They give tester learner pairs for more concept classes, such as intersections of Hall spaces, constant depth circuits, decision trees, and so on. And they also study more distributions, such as strictly sub-exponential. And they also present connections to pseudo-randomness, to fooling, about which I was speaking a bit earlier. And there's also been plenty of other work that focus now on semi-agnostic learning. So instead of opt plus epsilon, you only shoot for O plus epsilon. So there it was known that algorithms with runtimes poly in n and 1 over epsilon can exist. And unlike in the fully agnostic learning setting where where we think the exponential dependence on 1 over epsilon is necessary. And additionally, GKSV23B succeeds for a wide class of distributions. So there's a class that contains more than one. That's a wide continuous class of strongly low concave distributions, and the testing algorithm we present in that work accepts every single distribution in this class. And let me finish with some open questions. So, can you find more tester learner pairs for other classes, for example? For example, for the class of submodular functions, or for low concave distributions, or permutational invariant distributions? So what are some other classes of distributions that can be handled this way? And what about assumptions? What assumptions hold for real-world datasets? Can we design tester learner pairs that we can run on real-world datasets and verify that assumptions really hold there? And finally, it would be very interesting to know what can be done beyond learning. So what are some other algorithmic tasks that depend very strongly on some assumptions on the data distribution, and can we have also test these assumptions for those other tasks? So thank you very much. Please email me if you have any questions, and looking forward to seeing you at the conference.